Hello and welcome. Today we're going to talk about the Fourier transform and the diffusion or heat equation. And what we're going to do is use the Fourier transform to help solve and really not just solve, but to understand what's going on with the heat equation on the line and see if we can gain more insight about what the heat or diffusion equation is doing. So let's write this down. Of course, the diffusion equation is UT equals duxx, where d is the diffusion constant, like that. And if we're talking about the heat equation, this would also be just that heat conduction. And then we also have an initial condition, u at x, t equals 0 equals f of x. And now we're on the real line, right? So we have here's our real line, goes off both directions, somewhere in the middle 0. And we might have some initial distribution of, that's some sort of mass density. F of x. And so, of course, the total mass is going to be just the integral over the real line of f of x dx, and you get the total mass. So the idea here is we want to think of this mass density as being, perhaps like some sort of dissolved substance in a liquid or a fluid, and what's going to happen over time is that this is going to spread out. So we know that's the basic qualitative feature, is that this is going to spread out over time. What we want to do now is talk about what exactly, how exactly do we describe that spreading out over time? How do we capture what that is exactly? We know that it's going to start moving this way, and it's going to start moving this way, and the high peaks are going to sort of drop down. And these peaks are sort of going to come up a little bit, maybe, as they're coming down. And that's going to drop down. And this is going to spread out like that. All right, so we know that's the basic idea behind diffusion. But let's see if we can get some more insight. And so, the usual separation of variables leads you to a p of x equation. And it's going to be parameterized by our omega, just like we've seen before. And we're going to do the complex exponential form, and we'll say it's e to the negative I omega x. And here we're thinking about omega being on the entire real line. And so you can see if this is a negative number, this omega, this becomes a positive exponential. So we get both the positive and negative exponentials by doing this. And then the I, of course, makes it a trigonometric style function. All right, so that's this, and that's parameterized by this parameter. And then we have q of t that's also parameterized by omega, and that is going to be e to the I omega squared dt. All right, and that will also be negative. Okay. Oh, that's not quite right. I should have said e to the omega squared dt, right? There's no imaginary number there because the ODE was a first order only. All right, and so of course we put those together and we get these basis functions parameterized again by omega. U of x of t is going to be e to the negative omega squared dt e to the negative I omega x. All right, and in order to get, so this is a basis function. All right, and what we want to do is, of course, do a linear sum. And that linear combination is going to be u of x of t, and this is to create a general solution. This is going to be the integral, and this weighted sum, this linear combination, will be an integral now because we're talking about parameterization by a continuous variable of c times omega, and this represents a kind of a Fourier coefficient. times our omega, our u omega functions. So there we go. All right, so the idea now is we want to talk about how the Fourier transform plays a role here. And we know that, first of all, we know one thing. We have an initial condition. So I'm going to actually go to the next page here a little bit. So we have this. This is our general solution. And that's going to be over the entire real line. We can just put a real symbol there. And C omega e to the I omega x e to the negative, so there'll be a negative there too, e to the omega squared dt d omega. All right, and this again was our u omega x comma t function. All right, and so what we wanted to do is find out what weighted sum, and so of course we use the initial condition, and that is that f of x is equal to u of x at 0, and that becomes c omega e to the negative I omega x d omega. And that, of course, is precisely the definition for the inverse Fourier transform of c omega. And because we know that if I take f of x, which is given to us in the problem, and if I transform that using the Fourier transform, it's going to hit some function, which is, of course, c omega, and then we're going to go back. F inverse of c is going to get us back to omega. All right, so that's our two transform pairs, and so there's our nice result there. Okay, so this, we've derived this before, but the idea was this wasn't really very constructive. It didn't really explain, what we could do to really crank this down to something that was understandable. So the next thing we're going to do is do exactly that. So recall that we'll get a new sheet of paper here. So again, our general solution is going to be, and we'll just put this. So it'll be e negative I omega x e to the negative omega squared dt d omega. And recall that c omega is the integral, it's the inverse Fourier transform of f of x. But for notational, so we'll just leave that right there for now. E to the I omega x dx. And we usually put a 1 over 2 pi out the front to keep, so the math works out right. So there we go. That's how we do it. And now what I'm going to do is actually substitute this in. It's up there. We're going to do a little work to get this down. So we know our solution, u of x of t, we want to get some perspective on what this is, because this right here, it doesn't quite explain what's going on. It seems like we're sort of, being a not a very good magician here, where we're putting a bunny in a hat and then pulling the bunny right back out and pretending it's magic. But it doesn't seem to really give a lot of insight into what's going on. So let's see if we can help understand more about what this thing is doing. Okay. All right, so what we're going to do is actually put this together. It's going to be an integral from negative infinity to infinity. I'll just put these symbols out there. And now wherever I see a c omega, I'm going to actually put this in its place. And just so I don't confuse myself here, because we have an x in the problem already, I don't want to use x as my variable of integration, so I'm going to use c. Just as a notational convenience, so I don't get screwed up. All right, so there we go. And then we have to put this there. Times e to the negative omega squared dt d omega. All right, so we have this integral on the inside, and of course that is exactly c omega. But now we're going to move things around and try to make a double integral out of this over an area of c omega space. It's going to be, of course, the entire plane in c omega space. And we can do that. We can put the 1 over 2 pi out front. And negative infinity to infinity. And now what I'm going to do is actually switch around and put the omega integral inside as much as I can. So I'm going to actually bring this c thing, because this is a function that doesn't have any omegas in it. And then everything with an omega in it has to go inside of this other integral here. So that'll be an e to the I omega c, e to the negative I omega x, e to the negative omega squared dt. Okay, d omega. So I'm going to maybe even do this. So sorry, oops, we made a mistake here. That's d omega and then d c on the very outside. So there's that. I'm going to write this yet again, just to keep trying to herd this together to make it make more sense to you. So we have an f of c. And so the idea here is what we're trying to do is make this more in terms of f. So we want to see how f is going to change and morph into our solution later on in time, right? So here's our initial condition, and we're doing something to it with these integrals. And out on the other side, we'll pop the solution as time goes forward, right? And so that's really what we're doing here. All right, so I'm going to put that 1 over 2 pi there. And now we're starting to see a little clearer picture. I see that these are there's common factors of I omegas there. So I'm going to put that time exponential, negative omega squared dt, e to the negative I omega, and then what I'm going to do is put inside of it a x minus c. Okay, and then what I'm going to do is put that d omega there, and then d c. All right, and there's our integral. And what I see here is that there's really, it's a function of we're integrating over omega here. So omegas will leave the problem the minute this integral is done computing. And what comes out the other side, the only variables that are coming out the other side are things involving t. That's a parameter within this integral. There's also x and also c. Okay? And so I'm going to actually label this function here to be, this whole function here, to be what I'm going to call capital G of, if you look at it, really x and c are actually, it's the difference that matters, so we can actually consider them as x minus c. And this goes a little bit different notation than what your book does, but I think it's a little cleaner. All right, so that looks a little nicer. And now we see that we have this integration operation and this special function g, and we take the initial condition and we do this integration on it, and out pops what happens later in time to that initial condition, right? And again, our idea here is we have some initial condition, and it's going to start spreading out and doing what diffusion does to a mass distribution. And so now this action on this function here represents that process of diffusion. So let's try to see a little clearer what's going on. This still isn't really quite clear what this function is. So let's go check a little bit more. So I'm going to write down our result like before. U of x comma t is equal to the integral negative infinity to infinity of f of c g of x minus c comma t d c. And if you remember from before when you saw convolution integrals, this is actually a convolution. And we can actually write this as a symbol. We'll call it f star. g, and the result is going to be a function of x and t. Okay? All right, and so what is this doing? And so, again, we have to write down what g is. G of x minus c t was this integral 1 over 2 pi, integral negative infinity to infinity of e, and let's see if I can get my, I can remember my notation here a bit. It was going to be negative I omega x minus c minus d omega squared t, and d omega. Now recall from before, you see that this looks like a polynomial. In omega. There's an omega squared there, and then there's an omega there. And remember, within this integral, x and c and t are all parameters, and d as well. So this polynomial in omega, we can complete the square. And do a bunch of other calculations. And I think I'm going to skip this calculation right now and leave it as an exercise. And in the previous video, we actually covered how to do this. And if you want, you can go through it yourself. But it turns out there's a very nice result. This sort of integral becomes, we can actually write down the result. And I'll just skip right to the answer here, which is 4 pi, 1 over root 4 pi times dt, all under the square root, e to the negative x minus c squared all over 4 dt. Okay, so this is the function, and what they call this, so of course this is a Gaussian function. In x, okay? Or more aptly, x minus c, right? All right, so if I like set c to equal 0, or any number anyway, and then I set t to be equal to some fixed number, so I'm going to just set it equal to 1, let's say. Then of course what we'll get is something of the form g of x 1. It'll look a little like, neglecting this term here, it's going to look something like negative alpha x squared, where alpha will be related to 1 over 4 dt. So this is this Gaussian function that we're so interested in. And so let's recall what these Gaussian functions look like. Of course, they're sort of bell-shaped. And in general, they're going to be centered around whatever value c is. Right? All right, but so right now c is equal to 0, so we can just put that there. Now, what about this parameter alpha? You notice that alpha is actually, in this case, related to 1 over 4 dt. All right, and again, we're neglecting this part. This is going to do something important to the function as a whole, but the real engine of the function, of course, is the exponential. So alpha, let's see. Now, if alpha is, so if t is small, that means alpha is big. And when alpha is big, what you're going to have is, that means the function is going to decay rapidly to 0. And that means you're going to have a sharp peaked bell. So it's going to look very, very sharp like this. And now as time gets bigger, and that means that alpha gets smaller, and that means a broader bell. So something like that. And as time keeps getting bigger and bigger, the bell shape will get broader and broader and broader and broader like that. Okay. So the idea now is this looks a lot like what we think diffusion would be. That if we were have a small drop of some dissolved substance that we drop into a big pool, like a swimming pool, the concentration right near that drop, of course, would be very high, and it'd be zero everywhere else. And let's say that drop, it's like a drop of food coloring or something. And as time goes on, that food coloring is going to diffuse through the medium and get more and more mixed up and swished around until it's spread out over the entire expanse of fluid. All right, so that gives you a much clearer picture of what's going on inside this equation. So now let's to close this out, I want to do one more thing. So what we have here again is we have this function g of x minus c, comma t, and f of x is our initial condition, and we now know that the solution to the diffusion equation is what happens to this mass distribution over time, right? And the question is, what happens to the mass distribution over time t greater than 0. We want to know what happens as time moves forward. And now we know that u of x of comma t, that distribution of mass, is going to be our initial mass convolved with our function x minus c t. Oh, sorry, I should just put this right like that. Call it x comma t. Okay, and so really this convolution is this action of transformation from past to future. All right, so as the initial mass distribution evolves, this function g is what drives that evolution. It's through this action of convolution, this integral, which we can write down as okay. So what's going on here then? Let's see if we can get even more perspective on this. So again, g has a very specific form. It is going to be, again, it was root 4 pi dt e to the negative x minus c squared over 4 dt. Okay, so this function, so what happens then, the question then is, what happens at t going to 0 from the positive side? We can't go the other way because we only have information about the initial condition, not before the initial condition. So what happens then? So you notice, like we said, as t is getting smaller and smaller, we get a sharper and sharper peak in our little bell-shaped curve. And so what happens is this thing, so the limit t goes to 0 from the positive side of g of x minus c of t. This becomes, the limit of it is what we call the delta functional. Okay? And the delta functional has a really nice property. This is called the delta functional. And it's the process of this sharply peaked Gaussian function getting taller and taller and taller and taller and skinnier and skinnier and skinnier and skinnier until eventually the magnitude, the peak magnitude, will go up to infinity. And so it no longer becomes an actual function. It's actually not a function at all. So we call it a functional. But you'll see oftentimes in practice people still call it a function, even though it's a function that essentially is equal to infinity at x is equal to c. I'm writing this down. This is a fairly a fast and loose definition. It's not a concrete definition, and it's 0 elsewhere. Obviously, this isn't a real function. In fact, this makes no sense. But that's the idea. That's the picture we have in our head, is that they have this one point that's infinitely large, and it's 0 everywhere else, even though infinity isn't really a valid value for a function to have. It's not a value at all. But we also have this other property, which is more concrete, the property of that if I take an f of x, and if I convolve with the delta functional, so sorry, I already put the convolution symbol there. It just spits out exactly, sorry, that has to be c there. It spits out exactly f of x. And the idea here is that f of x is equal to the integral from 0 to infinity of f of c delta x minus c d c. And this, of course, is the inner product f with delta. So the delta functional is this notion that's sort of like a function, but it's a function when you inner product it with respect to some other function, it spits out the function at the specific value x. So it will produce the function value at a certain point x. All right, so this is really nice. So this is a neat idea, this idea of a delta functional, and it's hugely important in applied math to use delta functionals. They become very important for many very practical problem-solving techniques, as well as means by which we do numerical computations. We use the delta functional quite a bit. So what I want to do now is talk about if this is the idea. So if our function here g, and I'm actually going to define what g is. I'm going to call g. Now we're going to call g. I've said that it's sort of an action of transformation. Well, we actually have a name for that. This g is actually called the diffusion kernel. Or the heat kernel. So the heat kernel, or the diffusion kernel, again, this does represent the idea of a kernel as being like the seed, and that's the notion we're trying to invoke here. It's the seed by which everything grows out of. So the kernel, if you plant the seed f, g, this kernel generates what happens in the future. It makes the initial condition grow and evolve and change as time goes forward. So that's a really nice idea. So now let's actually do like some little experiments on what exactly the diffusion kernel does. And so now that we have the idea of a delta functional, so now I'm going to do a little experiment, a little thought experiment. And say, well, if f is my mass density at t equals 0, I'm going to talk about that very specific mass density of doing a drop of food coloring in a giant in a 1D medium. All right, and so of course, and I'll give it a specific. So I'll say it's actually 100, maybe a 10 gram drop of mass, and it's at a very specific point, at a point x equals 10. Or no, let's go with x equals 12 just for fun. All right, so we have 10 grams of stuff, and it's so highly concentrated. It's in a very tiny drop relative to the spatial scale of our system. So we're going to effectively say that f of x is actually the delta functional times 10, because we have a 10 gram, x minus 12. All right. So our total mass of all of our mass in the whole system is going to be, of course, the integral over over the whole entire space of f of x, right? Because f is a mass density. If I integrate it, I get the total mass. And of course, that's going to be 10 times the delta functional at x minus 12. And again, we can draw that as sort of like here's 0, and somewhere out here is 12. And I can kind of draw it like it's sort of like, maybe a little lollipop. Like there's just this little point of mass right at 12 dx. And because we're integrating over this interval, and our function is 10, and it's going to be 10, and basically then it just becomes 10. So our mass, of course, is just 10 grams, and it's just highly concentrated at a single point. All right. All right. So now what we want to do then is use this idea to find out what happens later on. So what happens is t goes to a positive value. All right. So of course what we do is we use our diffusion kernel as so, like this, and we're going to take our initial mass density and convolve it with our diffusion kernel, and that becomes an integral from negative infinity to infinity of the delta functional times 10 x minus 12 times, and we'll write it in there, it's going to be 1 over root 4k, 4 pi dt e to the negative x minus, we're integrating over c, x minus c squared, all over 4 dt, all right, d c. All right, and so now, of course, this functional is 0 everywhere except for at that point c equals 12. And of course, just like up here, remember that anytime we have an inner product, we can think of this as an inner product of delta with our function g, and it's going to be at 12. So what we're going to do is essentially say require that x goes to 12, and the answer then, our c goes to 12, and we come out with a 10 times 1 over root 4 dt e to the negative x minus 12. So everywhere we see a c in here, of course we just plug in a 12 squared over 4 dt. All right, so of course for time small, we're going to get a sharp little peak right around x equals 12. And as time goes forward, it's going to broaden out a little bit, like that. And then it's going to broaden out even further, like that. So we see that's what we call the heat kernel. And so now, again, the fundamental action is this action of convolution. And we have this special function now that gives us the answer for all time. All we have to do is perform a convolution integral. So you give me an initial condition, and I can show you what's going to happen. And we did a little experiment on a very specific one, which is like if we just have a drop, this drop of food coloring or whatever is going to spread out according to this thing. And we see that d, that diffusion constant, then sets basically the rate at which it expands out. If d is a very small number, it means it's going to expand slowly, and if d is a large number, it's going to expand much more quickly. And of course, now if I go to the idea of, I'll go back to the general idea of here's my f of x as some mass distribution, like so. You can think of this mass distribution as actually being composed of a bunch of little point masses all very, very, very close together. And each one of those is essentially independent, and we can handle independently and say that there's just a little bit of a heat kernel, or this diffusion kernel spreads out that little mass there, and here it spreads out that little mass there, and here it spreads out that little mass there, and so on and so forth for all these little masses. And essentially the action of F convolved with G is this process of dispersal a process of dispersal of each point x's mass through mixing with neighboring masses or neighboring positions. So there's going to be a little diffusion there from this little point mass, and there's going to be a little diffusion from all of the point masses, and they all start sifting, mixing or sifting, and shoving around. And of course, here, this mass right here is going to be sharing masses with its neighbors, and now those neighbors, of course, are going to be sharing some mass back. But you see here that, of course, there's not much mass to share this way, so more mass is going to go that way than that way. And so that's how we get that general spreading out. It's because although each neighboring region is sharing amongst each other regions of lower concentration, i.e. these points at the foot or the further out, they can't share as much back as they're going to be getting from their neighbors, which have more mass. So in general, areas of high concentration will be sifting and sharing more going outward than there is going back. So that's what generates this process of dispersal, and it's through the act of a convolution. So thank you very much.